So I started the recording now. Okay, welcome you all again for the Advanced Processor Architecture course. And the background image that you see is the temple in South India. It's a Meenakshi temple. Let me introduce the course before we start detail into that. So this is a problem. Okay. Sunanda, are you seeing some window in the beginning, in the front, blocking the?
Yes.
I don't know. I don't know how to remove that from the shared application. One second, I'll pause the recording. Okay, so this is going to be an online lecture and with 10 minutes of break in between. And there are no tutors in this course. I will manage all the course related activities. Okay, as a course objective is to teach you about processor architecture in detail. And there are some prerequisites which are the courses that I have handled earlier: digital design, computer organization, microprocessor and interfacing, OS. And of course, all of you are expected to have a good knowledge on C. And for explaining some of the concepts in processor architecture, I am going to use ARM assembly instructions. So I will explain each instruction when I am using that. So you don't have to remember every instruction, but just to give you a introduction that we are going to follow ARM instruction syntax. So let me quickly go through the objective to understand deeply into our architectural concepts. Lots of parallelism concepts which are implemented in the architecture, then different parallel architectures, pipelines, and what the instructions when they go through the pipeline, what are the hazards they go through and how they are avoided. We'll talk about that. Then there are some architectural in details. Again, this is a problem. One second. Okay, so there are some instructions which are to be scheduled in the hardware dynamically, which is done by hardware. We will talk about that also. Then branch prediction. Then one important concept here in multiprocessor design, where there is going to be cache on every processor and they need to be coherently managed. So there are some coherency issues involved, and there are some protocols to avoid those coherency issues. We will talk about that. And then there is bus interconnection schemes within the processor connecting multiple processors and memory. So this is a hardware bus inside the processor. So just at the end of this, we are going to use some online simulation tool. You are going to be doing it part of, it's not during the course. You have to do it offline, try it out, different concepts and different configurations there. We will not use this tool in the course, during the course. Okay. So these are the syllabus which is covered which is given in the course handout. We will have first 6 sections followed by one test, and then the remaining session with the final comprehensive exam. Just to brief you, attendance has some element of evaluation component. So around 20 marks is given to that. Okay. So this is the breakup of marks assigned. You get 20, and active participation means being active in the class. I can make out, and I will be conducting some polls to get your answers. So that is the way I can make out whether you guys are just listening or just online and then not doing it. So uh, I will make sure that you follow everything that I teach from the beginning. If you listen, I can assure you that everything will be understood. But if you miss me in the middle, it's going to be difficult. So today's lecture is going to be very important because I am going to give you the overview and the introduction which is required for you to understand the remaining section. Okay. So I hope this is self-explanatory. Let me not spend time on this. Okay. I have already shared the link. Okay. Okay. So this is the book which is going to be followed closely for this lecture. Okay. I have, you please look at the mail that I have sent. And we have a hard copy, but you may not be having access to that for the reference 3. Okay. So let us now go into the course now. Hope you can see the session 1. Can one of you confirm it? Okay. So this is the course coverage. And today's focus is going to be the following topics. So we will have a break somewhere around this place, half of the session. Okay. I will keep a tab on the time also. Okay. Now, what is computational models? Let us just understand before we go detailed into computer architecture. See, the purpose of having a computational model is to be able to run a computational task. It could be any program or simulation tool, whatever we develop. Now, how do we write this computational task? We normally write it in a C program or a Java or assembly. Whatever we develop, we need that to be run on a system. Now, there are two things involved here. One is we want to write the programming task, for which we need a tool. It's a programming language tool. Most likely, most of the time, we use a higher level language to write an application or a program, and we want to make it to run on the hardware. Now, the computer architecture is an implementation tool of our computational model. So we have a computational model which is specified with the help of programming languages and run on a computer architecture which help us achieve what we want. So this is a kind of an implementation tool which helps you run our application. So when we define a computer architecture, we need to worry about what is that going to be run on it. What we don't worry about which programming language as such, because we convert every programming language, either it is Java or C, C++, anything, we convert it into assembly language, and finally the architecture allow us to run assembly programs. So basically, computer architecture definition or any decisions are not directly bothered about which language is running on it, because finally what is going to be run is assembly program on the architecture. So what we do, computational model to programming language definition and then architecture definition. So this is the flow of what we want to achieve. This is how we do it. Now, we know that programming languages, higher level languages, as well as assembly language, support us in defining variables and storing them in a memory, modifying the values. So we will be able to successfully do some computational job on a given architecture. Now, it is not that only variables should be modified. We should be able to change the control flow of the instructions, because based on the variable values, we may take a different decision and run a different set of procedure or a set of instructions. So we need control of execution sequence. So there are some instruction both in programming higher level programming languages as well as in assembly language to achieve change of flow of the program. So what do we call these languages? As imperative languages. That means any programming language, you might have studied few of them, they have these features. That means we should be able to define variables, modify their values, and store it in the memory or a file system. And we should be able to change the flow of program as we proceed with the execution. So in a summary, this slide, what I want to tell you is, if you want to do some computational activities, we need a specification tool, which is a language, and we need an implementation tool, which is an architecture, which enables the programs that we have written to be run on them. So our focus in this course is not to talk about programming languages, it is about architecture. And how does computer architecture help us in achieving this goal? Now, let me just briefly give you an overview of assembly language, which all of you have studied and written a lot of assembly program. As you know, any higher level variables, or in fact, if you need to be modified, it has to be brought into a register. So the variables are in memory. It is brought into a register on the CPU, and it is operated upon, finally written back to the memory. So basically what the processor executes is set of assembly instruction. Now, what does the tool assembler and the linker do? It converts the binary form of this assembly instruction and stores it in the memory so that processor can read it from the memory and execute it. So this is the job of different tools that we use to make the processor execute our program. So you guys already are aware of this. A computer programming assembly language, what does it do? It's a machine code instruction which is finally stored in the program memory. Now, because assembly depends on machine code instruction, every assembler has its own assembly language. So it has got its own syntax. Now, each processor family has its own architecture and its own assembly language syntax. So assembly language is nothing but a programming view of the architecture. So for example, if you are using a x86 or a ARM family of processor, it has got its own assembly instruction and its own syntax. Only that assembly instructions are understood by the processor when it is executing them. Okay, now let me just briefly give you overview of the courses that you have handled, which are corresponding to which levels of the abstraction. This is the computing system. At the bottom level, the core IC chips are made out of resistors and capacitors and transistors. You studied about circuits, that is the basic electric circuit course way back 4 years back. Then we studied about electronics 1 and 2 and the labs, which are basically the basic building blocks of our circuits. Then we studied digital design, which is an implementation of basic gates, logic gates, and the ALU multiplexer, and those concepts were studied there. And then we studied about computer organization course, which is about memories, different kinds of memory, DRAM, SRAM, EEPROM, and what are their characteristics. Those things we studied. Then we wrote a lot of assembly program using Arduino hardware. Whatever you learned during these courses is going to be very useful for you to understand this course. But I don't expect you to remember everything. I will touch upon all the basic concepts so that even if you think you don't remember any of this, what you learned, you will be able to follow this course. So don't give up when I say that you should know all of this to understand this course. I will make sure that you don't miss anything. But I would be happy if you know this because it is going to be useful for you throughout your life. Then we had a course on operating system, which is purely a software which is running on top of architecture. And then recently we had a systems programming course, which is an interface between the application program and the OS. Then way back, we also studied about computer networks. These are the courses I handled, and we are going to be now concentrating on this area, which is instruction set architecture. It is not specific to any particular instruction set architecture. We studied here about Arduino architecture, whereas in this course, we are not going to be specifically studying about any particular family of processors. It is a generic concepts which are applied on various processors. It could be ARM or Intel or any, even Arduino. All of them follow these concepts in their implementation. So this is going to be the focus of this course. Now, just to tell you, basic electronics is here, computer architecture is on top of it, then assembly language programs run on this, and we use operating system as an intermediate library for us to program the hardware. So we normally work in this application programming level, or sometimes when we are developing something inside the operating system, we will be working at the OS level. So programming language, higher level programming language at the top. This is all hardware and the whole thing is software. So I will not go detailed into this. These are all the different behavioral descriptions of each of those levels. Okay, now let me go detail into what is computer architecture. See, I hope you understand this. This is a basic electronics, and then computer architecture is here. Please remember one thing, computer architecture and processor architecture, they are almost same, but with a little bit of difference in them. Now let me clarify that. Now, computer architecture abstract system is like this. This is the more detailed one. As we go here, we are getting an abstract view of the things here. It should have been the upside down, but the book is giving in this order, so I have given you in the same order. So we are increasing the abstraction level. What I mean by abstraction means we forget some details when we increase the abstraction level. Okay, so for example, when you are at this level, we will worry about how does the ALU function. Is it done by full adder, or is it done with a what implementation is done, which gates are used. We talk about that when we are in that level. Now, once we talk about ALU, we do not worry about the inner details of implementation. We talk about how do I control the ALU to perform different operations? Maybe a compare operation or a logical operation or a shifting of bits or an addition, subtraction, multiplication. So this is at the functional level. So we are increasing in the abstraction level. As we go further up, we talk about architectural level. In this level, though we bother about what ALU is doing, but we don't go into the details of how is it implemented. And here we bring in some registers, and partly cache memory also is considered to be part of it. But all the bus interface and how does the ALU is connected to the register and how an assembly instruction get executed in the processor, that is what going to be our focus here. Okay. And then we go into the details of chip level. Here, different processors are there and they are all connected through buses and memory. So here, this memory is the external memory, not the cache memory we talk about. And in this level, we talk about system level. So this is architecture level where inside the processor, what is happening is our concern. When we come to system level, we worry about how a processor is interfaced with the memory and how do they communicate. And in this picture, you can see that it's a multi-processor system with a multiple memories connected to the processor. So we talk about a lot of cache coherency and system level details in this case. So our course, this computer architecture, processor architecture course is going to be bothered or can't spending more time on these two levels, architectural level and at some system level. Okay. Now, this is just another view of how a processor architecture is defined at different levels. If you see, abstraction is going up here. We worry about transistors, capacitors, resistors here. And using these basic components, we build gates, latches, flip-flops. This is what you learned in digital design. And then functional level, we talk about registers, micro sequencers, that is how an instruction gets executed within the processor, and ALU, multiplexer, those concepts are discussed. Then we come to cache coherency and other protocols involved which are related to hardware. This is purely closer to hardware. Then we talk about CPUs, memories at the highest architecture level. So this is another view of the architectural implementation detail. Okay. Now, let me give you a definition of what is a computer architecture and what is a processor architecture. How does it differ from each other? Now, computer architecture is a set of rules and methods describe the functionality and the organization of a computer system implementation. So it involves not only CPU, also the peripheral units, memory, the whole computer system. In our laptop, a computer system is a whole thing including the motherboard and keyboard and display and the OS running on it. So here block diagram is CPU block diagram is shown, and the solid lines are the flow of data and the red lines what you see are the control. So when the data is flowing through the CPU, there are so many control signals controlling the way the data flows. It could take any path based on the control signals from memory to CPU or through register. The data flow is controlled by the control signals. Now, there are three subcategories inside a computer architecture. One is instruction set architecture, which defines the basic instructions. How does a processor execute those instructions and how is it defined. This ISA also includes either the processor is a 8-bit processor or a 32-bit processor or a 64, what kind of NDNS is used while a processor is reading from a memory or storing some data into the memory, and then different addressing modes of memory. You might have studied in the ARM course or even the microprocessor interfacing course about different addressing modes: indirect addressing, direct addressing, indexed addressing. Those are all different addressing modes which all fall under instruction set architecture. There are different families of processor. You are aware of this. Maybe MIPS may be new to you. MIPS is a microprocessor without interlocked pipeline stages. That's the expansion for it. Do not worry about what I mean by this. We'll study that soon. Then microarchitecture. This is about the organization, the computer organization, which we studied. This describes how a particular processor will implement the ISA. See, ISA is a specification of different instructions. It doesn't talk about implementation aspect. Whereas in the microarchitecture, we implement the ISA into a processor. So suppose, for example, we say that ARM processor is using some particular register for stack or 13, then that is the decision taken at this level. Okay. So ISA is a specification of an architecture, and microarchitecture is an implementation of what is specified here. Now, just want you to understand that you know what is CISC and RISC and CISC. x86 processor is actually a CISC family, but the recent x86 family processors like Pentium or whatever has come later, they all execute RISC type of instruction inside the processor. So they convert every 6 instruction into RISC instruction before execution. That's what happens on any Intel x86 family processors. And then system design. We talk about how CPU is interfaced with different hardware. It is about cache, memory, internal buses, and including peripherals. Okay. Now, what is a processor architecture? I am showing you a block diagram of SoC, system on a chip. Here is a multi-core processor. As you can see, they have 2 levels of cache, L1 cache, L2 cache, and then there is one more L3 cache also. So there is a 3 levels of cache memory. If you recall, the L1 cache will be closer to the CPU and smaller in size compared to L2 cache, and of course L3 is larger than these two, and it is little away from the CPU. And as you see that all of them are inside the chip, and our RAM, which is called main memory, is outside the chip. So we have memory inside the chip, and CPUs are there which are fetching from mostly from the cache. They do not access any program or data directly from RAM. It has to come to the cache, and then they are accessed by the CPU. This you should remember throughout. Now, what does the processor architecture talk about? It talks about multi-cores also, as well as the internal organization and its interface with the memory and peripherals. Remember one thing, processor architecture only worries about the interface with the memory and peripherals, and not specifically about memory or peripherals. We do not include the details of memory and peripherals when we talk about processor architecture. So just to summarize again, ISA is part of the processor architecture definition, and its implementation is microarchitecture, which is also part of the processor architecture. Then multi-core design issues, which are basically cache coherency issue and internal bus interfaces with the memory and peripheral. So the processor architecture talks about these following things. Okay, these three. We do not talk specifically about this and any peripherals connected. So that is the difference. Computer architecture talks about this as well as peripherals. Processor architecture worries only about these three. Okay. Now, let me just briefly give you an overview, which you already know, a sequential model. As you know, all the programs are assumed to be sequential in nature. Von Neumann architecture, a model which all of you are familiar, which we talked about way back in first year or second year of your BE course. A normal computing system has some input from the peripherals coming in and the outputs are given. And the program is stored in the internal memory unit here, and it is accessed by the ALU, and the program is executed. It is always assumed that the programs are sequential in nature. That means the set of assembly instructions are stored in the sequential programming memory addresses, and the processor fetches one after the other and executes them. But do not assume that because we call programs are sequential, it always executes in a sequential order. There are some control instructions. Specifically, you might have heard about jump instruction, branch instruction, and return, call. There are so many assembly instructions which change the flow of instructions. So for example, in a higher level language, for loop and if condition and switch statements are good examples of control instructions. And we have sequential instruction also with some control feature so that we can change the flow of instruction sequence. Now, one limitation of this von Neumann model is code and data cannot be accessed in parallel. That means we have a single physical interface connecting to the code memory and data memory. So when the memory access happens, only code can be accessed or data can be accessed. This is a limitation of this model, and it was overcome with the Harvard architecture. You know this also already. There is a program memory and data memory. Both are given here. We have a physical interface connecting the CPU with them. And as you see, there are separate buses physically connecting the memory. So in a given cycle, both can be accessed in parallel. That's the major difference between von Neumann architecture and Harvard architecture. Now, this is already you are aware of it. Now, what do we gain? Let me just give you how does it help in running the program much better. As you know, a program memory is having set of instructions and the CPU is trying to execute, and one of the instruction could be accessing a data. So when you want to execute an instruction which involves an access of data, while we are accessing the next instruction, we need a parallelism involved. That means while data is being accessed from the data memory, a program can also be fetched from the memory for CPU to execute next. As you see, CPU is continuously fetching the program from the memory and trying to execute one after the other. Now, while executing one of the instructions, it may be a data access and it has to access the data from the memory. So these two accesses, if it can happen in parallel, we make the program run faster. So that is the advantage of having two different physical interfaces connecting to the data and program memory. Okay, now this name has come because of this particular architecture. I want you to read this. All current processors belong to this category. That means they are all hardware architecture because all of them have internal code and data cache memories with dedicated physical interfaces. So I won't be repeating this always. Remember that in our discussion, all the processor architecture is expected to have a separate internal cache of program and data, and which are connected to the CPU through separate interfaces. So they can be accessed in parallel. So remember, this is internal to the CPU or internal to SoC, and the actual data memory is outside. The main memory is outside, but we talk about data cache and program cache as an internal program and data memory. The CPU always reads from the cache. Whatever instruction it wants, it should come here first and then read by the CPU. Similarly, any data is always accessed from, this is data, this is cache. Okay. I hope this is clear to you. I will talk about it in the next, when we are talking about different architectures, you remember this concept first. Now, I'm going to quickly tell you how do we develop and run programs. This also I have covered in computer organization course, CO course. So let me just quickly give you the overview so that you guys refresh your memory. As you know, different steps are involved in program development. We edit the program using any editor, then pre-process it, compile it, and link it with any library functions which are not written by us. Then we load the program into the memory and execute. The CPU execute. So these are the sequence of operations we do before we make even one hello world program to be able to run on a architecture. Now, this is another view of what we do. Any variable that we define in a C program is nothing but a location in the memory, and any processor, if it has to do a count plus plus, it has to increment a variable. First, the variable current content has to be brought into the CPU. That is done with these two instructions. We get the address of the variable count. It is in the data memory. It could be in the stack or data. We need to get the address of the variable which is in the memory, and that is to be brought into a register. Then we do an indirect addressing. That means we access the content of the memory at this address, which is where our variable count is stored. This is decided by the linker, and assembly program is run by the CPU, and it is, if it has to increment a variable, it should first get the address of the variable and access the current content of the variable, then increment it, add instruction is done, then store it back. Okay. Now, let us see. Once we do this conversion, it is all converted into a binary opcode, which is stored in the memory. Okay. So this is how a typical C program gets executed by a processor. Now, just to give you an overview, any program needs to have the following things, which I have spoken about in OS course. We need a code area and static data area, which is initialized already. Then any dynamic memory allocation is done here. This is all in main memory. So any program to run, we need stack, we need heap and code. And this was covered in the OS course, so I will not go into the details of this. Remember that any variable, if it is a local variable, it will be here. Any global static variable is going to be here. And heap and stack, they grow dynamically while the program is executing. So this is the total physical address space of a processor. Okay, now just to recap, assume that a main program is the entry that you are all aware. Assume we don't have any variables coming, any command line arguments coming from the user. It starts executing from here. So we have a code and data here. Initialized static Decode variables are defined here. They're all already initialized with these values. These are all the content of executable file, and before we run the program, it is loaded into the memory, which is nothing but a main memory, and the processor is going to start accessing the code from here and execute the code. And we call the uninitialized data as BSS, and this is the expansion. You can see that this variable and this are not initialized. So you know that static variables are initialized to 0 when they are not specifically initialized by the user. So these are all filled with 0 to start with, and then as the program runs and modifies this variable, they get changed. So this is also loaded before the execution starts, before the main entry happens. And then heap is allocated here. Okay, so I hope this is all clear to you. We have studied about all this during our OS course. This I am giving it as a recap. In case if you guys still have any doubts, please refer to those material or ask me in case if you want any doubts to be cleared. Okay. I hope this is clear to you. Now, before we break, I just want to cover this topic and then we will take a 10 minutes break. Almost, I think we are touching 1 hour. So let me give you what is an architecture in a different perspective here. See, as I told you, CPU has program counter and memory address register and memory buffer address register, and there are IO registers. And this is the instruction register wherein the instruction read from the memory is stored and the CPU executes it. And you know that program counter points to the program memory. So in a main memory, you have instructions and data as well as stack, and different registers access them for execution purpose. And there is a bus which is called system bus connecting the CPU with the main memory, and program counter is loaded with the initial address. Based on the clock, it starts executing the instruction starting from the address given in program counter. So this is the flow of any instruction execution in a CPU. And data processing is involved, CPU as well as data memory. We have DRAM there, and then external storage is anything that you connect to the computing system. Okay, this you are all already aware. You should have this in back of your mind when we talk about different architecture. Remember that CPU is running in a given clock rate, and its job is continuously access the memory, fetch the instruction, execute it, and as per the instruction being executed, fetch the next instruction. So this is the job done by the CPU, and we are going to talk about inside of this CPU. Okay. Now let me just give you another overview of what CPU and memory have a problem. As you know that CPU advanced much ahead of memory, and there is a gap in the performance of between CPU and memory. CPU exponentially increased in its performance over the years, whereas memory did not catch up with that. So to bridge the gap between CPU and the memory, there are some techniques which are being used, which you are already aware, and which enables us to do this is a property of a program. This also I have talked about earlier, principle of locality. Any program that you run has a temporal locality and spatial locality. What I mean by that is any recently referenced location in the memory is likely to be referenced in the near future in terms of time. This is in terms of time, this is in terms of memory. And given an array of variables, they are all stored in a sequential address in a memory, in a data memory. If a variable is accessed here, the next variable is likely to be accessed soon. So this is called spatial locality. So this is the behavior of any program that we run in a processor. So this you are already aware of it. Given a program which is a for loop accessing an array of variables and adding it into taking an aggregate sum of them. So you know that array elements are spatially distributed. So because we are doing a for loop, within a for loop we are accessing the array, it is going to access the element 0 first, then 1, then 2, 3. So you know that the variables which are located in the adjacent locations are being accessed one after the other as the program runs. So spatial locality and temporal locality are the example of these accesses, and instruction being accessed is spatial locality, and cycling through for loop is a temporal locality, because after one for loop is done, it is going to execute it again. So what I want to summarize here is the program that we write normally show these two locality of references, and which means that anything that has been accessed recently will be accessed soon, as well as any location which is accessed, the nearby locations will also be accessed in the near future. So because of this locality of reference, we overcome the gap between CPU and the memory's performance. How do we do it? This is the way we do. So we keep a faster memory close to the CPU and the slower memories with a larger size away from the CPU, so that anything that the CPU wants, either data or instruction, is available on a faster memory. So what happens? Every memory access is faster. That means even though there is a gap between the CPU's performance and the memory's performance, we overcome it by bringing all the required code and data close to the CPU. Okay, so this is the memory hierarchy that we follow, and we increase the performance and reduce the gap between the CPU's performance and the memory performance by organizing the memory this way. Okay, so this is completes our discussion on computer architecture. Guys, do you want a break now? Nobody wants it.
No.
No.
uh, let me know. Let me see whether I am able to see the chat. Okay. Yes. Yes. Okay. So Uh, 1 second. Okay, welcome back after the break. 1 second, someone is joining. So, 1 second. If you remember in the computer organization course, we understood how does a CPU work. So, I'm going to talk about that in the remaining session now to make you remember those things which you might have forgotten. Okay. So, we have broken the break already. So, let us start now. I'm going to show you, this is a simple interface of a CPU with a memory and IO system. What is shown in blue is a control units, which makes CPU interface with a memory or a IO with the help of sending some control signals on the bus. As I told you, for a CPU to execute program, it has to fetch the instruction from the program memory and then start executing it. Based on the instruction, it may access a stack memory or a data memory. So as you all know, the main memory keeps all the information, code, data, stack, heap, everything is here. And based on the type of the instruction being executed, that relevant memory is accessed. Though we call it as program memory, data memory, stack memory, all of them reside in the main memory, which is a DRAM, read writable memory. So in this section now, we will quickly recap on how does a CPU execute instructions. Okay. Now, a computer system is complex. We have a centralized control unit. Instead of centralized, we have a distributed control units because we will not be able to control it if it is a centralized one. So what I mean by distributed means there is some control units on each of those memory and IO units also, which interact with the CPU based on the requirement of CPU. Either memory supplies the data or IO unit supplies the data. It all depends on what address is given by the CPU. If the CPU is addressing some location in the main memory, this control unit understands it and then puts out that data on the bus. You have to remember that address bus and data bus are common.
Can you hear?
Can you all mute yourself?
No, no, sir. So I will show you in my situation first. There's a rain now.
So coming back on what we discussed, as I told you, the CPU's job is to keep accessing main memory as well as IO based on the instructions. Okay, that's just top level summary of what I want to convey here. Now, CPU continues to access instructions from the memory and executes them one after the other. Based on the program flow, the data is accessed, either global or data, local. Okay, now from the implementation perspective, we are going to talk about an unpipelined or non-pipelined implementation. See, this particular section is very important for you to understand the remaining sections coming. We will be talking about pipelines, too many things. So try to understand this. What I mean by unpipelined means there is only one instruction in execution within the CPU at any point in time. There are no multiple instructions within the CPU. What I mean by that is the CPU, as I told you, accesses the memory to get the instruction into IR. Now, once that instruction comes in, based on the type of the instruction, it may take one cycle or multiple CPU cycles. So, as the instruction get executed, based on the type, it may take one or two, but the next instruction from the memory is brought in only after the previous instruction is completely executed. So that is called unpiplined execution. So let me now give you some overview of that now, what I mean by that. So the control unit only decides how different operations are done by the register set and the ALUs. It is being executed using microprogramming. So what I mean by microprogramming is, and every instruction has multiple stages, which I will explain to you shortly. So for them to be executed, we need to generate set of control signals, different values. So every cycle, these control signals change. We store those different control signal values as microprograms inside the processor. Every instruction get executed by set of multiple microprogram instructions. That means different control signals are sent from after one cycle after the other for completing the execution of instruction. So I will explain to you with an example. So ALU does the arithmetic or logic operation, and register sets are the innermost temporary storage locations wherein all the variables are brought, all the results that computed by the ALUs are stored. They are all inside the registers in the CPU. And you know about flags also. There are carry flag, overflow flags, signal, sign flag, all those things. And there is some internal bus structure wherein data from registers are exchanged between ALU and different registers within the CPU. Okay, now let me give you overview of a register set. What I mean by register set is a set of registers. It could be 8-bit register or a 32-bit register or a 64-bit register. Now, to address different registers within the set, there is a destination register select signal. So the fact that there are 3 lines given, you can think that you know that there are maximum 2 power 3 registers that can be addressed. Now, as you know, ALU needs 2 operands. The inputs to the ALUs are operands. The operands to the ALU come from the register set. We can choose any of the registers within the register set as an operand. And you can have same register also as an input or different registers as an input to the ALU, which is coming out. This is data is going in through this selection, and through these register select signals, we choose one of the registers contents available to be available on these outputs. So now one more thing I want to share here. This register set is supposed to be having 2 read ports and 1 write port. Let me explain this clearly. As I told you, there are 8 registers within the register set. An instruction is being executed by the CPU with the help of ALU. ALU needs 2 inputs that are called operands, which are nothing but 2 different register values within the set. Now, for an instruction, take an example of add instruction. It adds two values and then writes the result back into the register. Now, the add instruction may choose any of the given registers and write the output to any of the existing registers. So that is a one single instruction execution. So if a memory register set has two read ports, that means in a given cycle, we can access two registers simultaneously. That means content of two registers are brought in at the same cycle. Similarly, once the ALU computes the result, the output can be put into one of the registers in the same cycle. So it could happen in the rising edge or a falling edge. It depends on the implementation, but within the cycle, it can happen. I hope this is clear to you. This is called multi-port register set. That means there are multiple ports giving the data out from the registers and one input port going into the register. And these are the selection signals to choose a particular register based on the instruction. Okay. So this is what is explained here. This helps the CPU to get two operands needed by an instruction from the register set while writing the result back into register set after the ALU computes it. Okay. So we call writing back the results into the register. Okay. The result of the arithmetic operation or a logical operation. Okay. So let me go further. This is the inside of a register set. These are all the registers that I spoke about. You see that there are only 7 registers given. The 8th, that is R0, is always assumed to be having a value of 0. So you cannot write any value into R0. Okay. In this particular implementation, do not assume that this is how every processor is implemented. I'm just showing you one implementation of a register set in a CPU. This is very, very basic implementation. So in this case, we have a R0 register, which is always 0, and all these registers can be written into and read from. And all of you remember in digital design, we spoke about how flip-flops are used for storing bits within the register. So it could be 8-bit register or a 16-bit register or a 32-bit based on the implementation. Now, this is the destination register select coming from outside. Based on the demux, one of the bit lines will be giving the signal, and actual result is available here. This could be 8-bit wide or 16-bit wide based on the width of the register set. So this data comes in and one of the registers gets written into. So this is how register is written into from the instruction. Okay, this is done by the CPU after the instruction execution is completed. Now I told you about two operands which are coming out through a mux. So it can choose one of the register contents to be available here. So there are some selection signal which I showed you. These two are there. Based on the choice, a particular register value comes out and the ALU performs the operation and the result comes here. Okay. So register contents go out ALU to ALU, and ALU performs the job and gives the result back. So this is how a typical register set in a CPU is designed. Okay. So let us look into the, one second. So let me remove all this. So you see that there are control signals controlling which register to be chosen for writing, and there are some control signals which are given for a particular register to be chosen for an operand. Now, one more thing, remember that these control signals are part of microprograms written and is all in hardwired is within the CPU. Based on the instruction being executed, these control signals are generated and the execution happens. So this is how a processor executes an instruction. Okay. So let us look at the next one. Okay, we just now saw what is inside this. Now outside control signals are shown here. This picture all of you must remember, which you have seen 2 years back. Now two operands coming into ALU, either it can be from register set or it could be coming from one of this. Okay, these are all input. It could be coming from PC or maybe instruction register. So these are all the inputs, and MUX chooses one of the inputs to be fed to the ALU, and then ALU is programmed with these three signals what operation to perform, whether it has to be adding it or subtracting or maybe logical operation is chosen. So input is chosen using this, operation is chosen using this, and after the result any shifting is to be done is chosen by this signal. Now result is available here. This result can go to any of the inputs. Okay. Okay, so I will show you some example so that you understand this picture even if you have forgotten the previous course what we learned. Okay, let me give you an example of one instruction here. One second. Okay, suppose, one second, I will show you. If the CPU has to access a program memory, the PC puts out the program memory address, and the content of program memory, which is nothing but an instruction opcode, needs to be brought into instruction register. Now I'm going to show you what is the flow of signal that makes it happen. Now first thing is a PC stores the program memory which is to be put outside the CPU so that memory can give you the data. The data in the sense actual program content. So this is the instruction fetch. In this cycle, what happens is you need to choose the PC contents as an input to the ALU, because it is not going to do any perform any operation on ALU, but we need to pass it through ALU because this structure is designed like that. The content of PC cannot come through any other means except through the ALU and to the memory address register. So I'm just showing you how does it happen. So we have PC content coming here and we choose this particular input coming out using this control signal, and 0 is fed here so that this is not getting disturbed. No, the content of this PC is not modified, and shifting operation nothing happens. So the actual address of the program is brought into memory address register. Now once the output is coming here, this particular control signal has to be chosen. That is done using this control signal, load select. So a particular control signal, which is shown in black, selects this register, which latches this value. So remember, the program counter is an address which is now available on memory address register, which is to be given to the memory. Now, address is here from PC, it goes out. It is a read cycle because we are reading a program from the program memory. And control unit chooses, it sets up the memory for a read cycle. And then address is put on the bus. PC, whatever is there in PC has come to memory address register, and then it's on the bus now, and memory reads it. So memory knows CPU wants to read from this address. So what does the memory do? It picks up the content in the program memory and then it puts it on the data bus, which is connected to memory buffer register. So a read cycle from memory is nothing but address coming out of the CPU and memory giving the content of the memory in that address. So in this case, we are reading a program. So program content is given, which comes here. And you know that a program has to go to instruction register. So which is directly connected, but unless CPU internally routes this to the IR, it doesn't happen. So we will see that in the next slide. So currently a memory cycle has happened and the program counter puts in the address, and whatever is there is on the address bus, and the memory has given the data, which is nothing but the program content. Now, what happens next? Here, program memory content is going into IR. Now, you know that the program is available here. It should be routed to IR. How does it happen? So there should be some controls modified, signals are to be modified so that this happens. Now, as you see from the memory, the program content has come. It is already connected here. So we need to choose D2 here. This is chosen as 0 and output is nothing but the program content. Now this should go here. It should not land into any other register. One second. One second. Okay, so let me come back again on what I was talking. We have the actual program content coming in into the CPU, and different control signals are set such that we are able to route it to the IR. So don't worry about how it is done. We use micro programming to achieve it. It is being done for every instruction. You have to remember that every instruction read goes through multiple cycles. That's what I want you to understand now. So on one cycle, address is put. On the next cycle, the opcode is read. In case the memory is slow, it may take more cycles. That time, the instruction cannot proceed. It has to be stalled. Instruction execution will be stopped until the opcode is read from the memory. So an instruction execution is not happening in this system in one cycle. It happens over multiple cycles because of the restriction that we can take only one instruction at a time. There is no pipelining of instruction here because you can see that there is no facility here in this CPU to store multiple instructions. only one instruction can be in the CPU, which is being read and executed. Okay, that's the summary of my this particular slide. Okay, so once the instruction, I told you that IR has to be chosen, so that is done by using this signal, and a particular instruction get read. So let me give you another example, which is a repetition of what I did in computer organization course. Suppose if you want to add R1, R2, R3, which is nothing but R2 plus R3 is going into R1. If this instruction has to be executed, you can understand that there is no memory cycle involved, because this instruction does not need any operand coming from the memory. They are internal to the registers, internal to the CPU. It's all available here. Now, but still, this also takes, in this case, it can be done in a single cycle, or see, if based on the CPU, 1 second, there is some distraction here. Okay, now, as I showed in this picture, R2 is coming from here, R3 is coming here, then we choose the particular control signal here. So, and then we choose D1 and D1, and then add operation. Finally, it has to go into a R1. So we need to choose R1 here, and we need to choose this particular play signal, control signal, that is 1, based on this value. See, you can let me remove all this and then show you what exactly the microprogram's role here. Microprogram here helps you to choose a particular input and choose where the output has to be written into. In this case, it should be written into register set and exactly at on R1. So we generate these control signals, this 0 1, this 0 1, and the add function, and this is also, we choose all this control signal so that this particular instruction gets executed, which is called microprogramming. This is done using microprogramming. Okay, so I hope this is clear to you. Okay, now let me tell you, if we are to read a data, so another one example I will show you, then we will go into the different topic. If you want to read a data from a data memory, what do we do? It's sorry, it's for the write cycle. So we are writing into a data. So from register content, it should go to data memory. We want to write into the data memory. Now, let me show you the instruction. It is a store instruction. The value in R2 should go into the memory whose address is in R1. That means the address of data memory is in R1, and at that address we want to write the result which is available in R2. So I'm going to show you how does the CPU do this, and you know that it is a write cycle. Okay, so basically address is unidirectional bus. As you know, the data bus is bidirectional, because in the previous example we saw that program opcode is flowing from memory to CPU. In this case, CPU is writing into the memory, so data is going to flow in this direction. It's a bidirectional bus. Okay, now how does the indirect addressing? So okay, this is called indirect addressing because we are addressing the memory which is stored, address is stored in R1, and what happens, the address which is in R1 is put on MAR, it is given to the memory, and we put the data which is in R2 in the MBR, memory buffer register. Remember here, both address and data should be given by the CPU one after the other. First address followed by data. Okay, so I have shown you what happens outside the CPU when a data write access is done. Okay, so let me erase all this. With this, I have explained you how does the CPU access the memory, program memory, and executes an instruction, and how does it write into the data memory or read from the data memory. Read from the data memory is, you can always understand it by looking at some different instruction. Okay, if you do not remember any of this and if you want to catch up on this, please go through the computer organization course. You can quickly follow them because there are a lot of examples given. Okay, so I'm not going to spend too much time on this. And before we end, I want to just explain some instruction cycle, what they go through, so that we are ready for instruction pipeline in the next section. Okay, so this is also whatever you know. I am going to repeat what you know. Okay, so let me tell you, an instruction execution is nothing but fetching and decoding. If it is an indirect addressing, access it from the memory, then execute the instruction, write back the result. So you can see that there are 5 steps involved. One is fetching the instruction and then decoding it. Based on the decode, different opcodes or operands are selected. Sorry, different operands are selected because only the instruction has the information about what are the operands are being operated on by an instruction. And once we do the decode of instruction, we know whether it is a memory read or memory write, whether it is a indirect addressing or indexed addressing. Based on that, this state the CPU comes into. So you have to read from the memory and then execute it. If one of the operands is coming from the memory, it should be read from the memory. Then only you can execute. Remember one thing, every instruction to be executed, it should have all its operands, input operands available within the CPU. If it is from registers, it can be fetched directly. If it is not, it is to be fetched from the memory, which is an indirect cycle. So fetching of instruction is first step. Decoding is the next step. Here only the CPU understands what is the instruction to be executed. Next is, based on the type of the instruction, it could be an indirect cycle or a direct cycle. So let me explain. This is an instruction which needs 2 operands and the result is written into R1. Now you can see that this instruction does not involve any memory access. So there is no indirect access as far as this instruction is concerned, because operands are available within the CPU. Both operands are available within the CPU. It's a direct addressing. Here, one operand is within the register, whereas this has to come from the memory. R3 only has the address and the content is in the memory, which is to be read before this instruction can be performed. So this operation has to be done. Accessing the memory is an indirect access. It's not direct addressing. So this is the difference between these two. So after the fetch decode, this may be there or may not be there based on the instruction. Then execution happens and write back. Again, it depends on whether the result has to be written back or not. Mostly it will be yes. So execution happens, the actual add operation is done, then write back happens. So these sequences you should be very, very clear about when we talk about instruction pipeline. The CPU structure what we saw here, does everything within the CPU one after the other in every cycle. That means one instruction is fetched and it goes through all the steps before fetching the next instruction. That's why we call this CPU as unpiplined or non-pipelined processor. That means it can execute one instruction at a time. In other words, we can also say only one instruction is in the CPU in one of these stages. The instruction could be in one of these stages in an unpipelined structure. You cannot have multiple instructions on different stages, which we talk about when we go into instruction pipeline, where multiple instructions will be in multiple stages at the same time in a same clock cycle. In this example, what we saw, only one instruction is in one of the stages. It cannot be in multiple stages. One instruction flows through these different stages and then the next instruction is fetched. This is called non-pipelined or unpipelined processor. Okay, let me explain one thing. I am not going to go into details of interrupt processing in this course. So this is the where I may be talking about interrupt. Remember, I mentioned this in the microprocessor and interfacing course that after executing one assembly instruction, the CPU always checks whether there is an interrupt. As you know, interrupt is some signal coming from the outside world. It could be due to some internal error, or it could be that outside peripheral wants the attention of CPU. So the CPU does not look at interrupt during the execution of instruction. After it completes one instruction, in this particular case, it checks whether interrupt has come. If there is an interrupt, the normal flow of execution is stopped and the ISR is executed, interrupt service routine. That means it will access from different location, it will execute different set of instruction. It will be in interrupt mode, and after it returns, the normal execution starts. So this is also one of the state a CPU can get into. So as I told you, instruction execution can be a normal program flow, or it could be an ISR routine based on the interrupt. So this is something which you should keep in mind. Let me quickly give you different states when an instruction get executed, they go through. Okay, first instruction fetch happens. You know what happens in the CPU, I have already explained. Then decoding happens. Decoding is nothing but understanding what is the instruction is about, whether it is an add operation or subtract, or is it a memory read or write. It could be one of them, one of the valid instructions of the CPU. Once instruction is understood, now it has to execute it. Before executing, it should access the operands first. As I told you, operands could be either direct or indirect. If it is indirect, a memory cycle has to be started, memory has to be read, operand has to be brought in. Otherwise, the operands will be within the register itself. So this indirect cycle happens based on the instruction type, based on the operand type. Once this is done, you have all the data operands ready. So the data operation or execution can happen. This is the execution portion. Once the add operation is done, we need to now write the result back. Some instruction may want the result to be written into the memory. In that case, indirect cycle again will happen because the result has to be written directly into the memory. In the ARM example, it is not possible. In a RISC system, you know that load and store are different instructions, and all other arithmetic logic operations always perform jobs taking the operands from the registers. So in the RISC architecture, we do not have memory cycles for writing the result back, because there is a separate instruction which is doing it, which is a store instruction. So normally a RISC system does not do a result back in a cycle in a when it is doing an arithmetic operation. Suppose if it is doing an arithmetic operation, the result is always written into a register. So this also you should keep in mind. I will clarify it as we progress. Now, once the result is written either into the register set or the memory, we have a interrupt check done, whether any interrupt is pending. If it is so, execute the service routine. If not, come back and execute here. Okay. So this is the cycle which an instruction goes through. So I will show you the same thing with the sample instruction. Okay. Add instruction. Now this is the instruction I have. I have a little bit complicated. Someone is on unmute. Please mute yourself. Okay. I hope you guys can understand what is this instruction about. Let me explain. There are some values in R3 and R4 may be an index into the address. We add these two to get a final address from where the operand has to be read. So this is nothing but an operand address by performing an addition. It could be an indexed addressing in a ARM processor. Okay. R3 is having the base address. R4 is having an index into the base address. That means you have a memory, you have an array starting here, and you are accessing a particular element of an array. That index is stored here. To get the address, we add the base address with the offset and get the final address from where the data has to be read. Please mute yourself. I want to keep you on mute. You should be able to unmute yourself so that you can interrupt me. Okay. So R3 and R4 are added and the address is generated and the content stored in that address is taken from the memory and register content is taken. They are added. Result is written back into R1. This whole instruction is at 100H. This is the address of program. Now, an instruction format is like this. Opcode tells you what instruction it is, whether it's add or move or any operation. And this talks about what is the register, destination register, and these two are the source registers or source addresses. Now, this is the instruction. From 100H, H is hexadecimal address, instruction. This content of the particular instruction is read from the program memory. It is decoded here and it comes to know that it is an add operation. Now it is performing address calculation. You can see that operand address calculation is performed here. That means R3's content is added with the R4 to find out the final address at which the data is available. Now, before performing a read operation from the memory, we need to have the address ready. Once address is ready, the indirect cycle happens by putting the address out and getting the data from the memory. Now, multiple source operands are not there. Now, you have the data from the memory available now. So, R2 is internally within the register, so it is available. Then you perform the addition, destination register is R1 and interrupt check is done, and if it is not, it comes through next instruction. So it is incremented by 4. That means this instruction takes 4 bytes of location. That's all. If you understand this particular flow, I'm sure you will be ready for the next section as well as the future sections that we are going to have. So you have to appreciate that there are so many things happen before an instruction gets executed. So that's the purpose of giving you an overview so that you guys are all ready for the coming section. Okay, so let me just summarize it now. This is the last slide. If you guys are waiting for me to stop. Instruction fetch, it is a read from the program memory. Decoding is decoding the operation to be performed. Depending on the type, either memory read operation is performed, operand fetch is done, then either it could be direct or indirect. If it is direct, it is coming from the register. If it is indirect, you have to compute the address and then get the operand from the memory. Once the operand is fetched, what we do? We get into the CPU and then execute it. We need the help of ALU to perform the execution. Once the execution is done, we need to write back the result. Remember one thing, whatever is the output of ALU, unless it is written to the register, it is lost. Whatever computation done by the ALU finally has to be written into a register. So this is an important part of an instruction execution. Write back the result. So with this, one instruction gets executed completely by the CPU. All this happen over different cycles in an unpiplined execution. If the CPU does not have a pipeline structure, hardware structure, then only one instruction can be read from the memory, and that one instruction goes through different stages before the next instruction is fetched. So we have come now to the end of the course session today, not end of the course. Okay, I have a homework for you if you are not done so already. If you remember, Professor Raja has shared a link of podcast sometime back, couple of days back. This is these two authors talking to each other about what they experienced when they went through the processor architecture design way back from 1970s to 2020 now. So please read this podcast as a homework part before you come into the class tomorrow. And I will share the recording of this section also. Those who are not able to hear the lecture completely, they will be able to download and hear at their lecture. So thanks for all of you to come in and start the first section of our course. I'm excited about this, and I want you guys to give frank opinion of whether I need to slow down, whether you are able to hear me properly, or the slides contents are okay. Please give me your feedback. I will also be sharing this PPT in a PDF form over LMS. Please go through that and ask me any doubts before the next session so that I can address it before I start out. And one more thing I'll tell you, this course is little difficult because I'm going to talk about some advanced features in the processor. Today's session is just an overview. So I want you to understand that and pay attention to the class. And I am making every attempt to make you understand the course, and I want the support from you. Then this course will be a great success. Okay, guys, thank you very much. I am going to stop the recording. You guys, if you want to talk anything or then you can do. I'm going to stop.